Hi all, in this video I would like to discuss the Jacobian for polar coordinates. So we're going to apply the Jacobian rule that we learned in the last video, and what we discussed that if I have an integral over a region as a function of x and y, and this is of an area, then I can rewrite this as some new integral over a new region r prime of f of two new variables u and v du dv. And what this often correlates to is going from a region that looks like that to a region that looks like that. And of course it would be a lot nicer to integrate a region that is rectangular or circular or whatever have you, as opposed to a region that might be arbitrarily defined by a bunch of functions that would make an iterated integral quite nasty. Anyways, what I want to do today is discuss how we can use the Jacobian. The Jacobian we learned is the determinant of a matrix, which is governed by a set of partial derivatives, dux, duy, or dvx, duy, dvy. Then we take that determinant, and then we get a constant. And then if I want to integrate something, I need to tack j in before the differential is a constant. So now we're going to look at the differential measure for polar coordinates that measures the small dA that we have for polar coordinates in multivariable calculus for integrals. So the transformation for polar coordinates, we go from xy to r theta. We go from something, maybe a rectangle, over to a circle, or something like that. So what we use is we use the following equations from earlier math classes, where we say x is r cosine theta and y is r sine theta. So now what we need to gather is a bunch of partial derivatives. We need partial x with respect to r, so dx dr. And if I differentiate that, I just get cosine of theta. And then I also need dx d theta. And if I do that, I get negative r sine theta. Then I also want to differentiate dy dr, that's sine theta. And then I also want to differentiate dy d theta. And that is going to be r cosine theta. So what we get now is the Jacobian is equal to this determinant of all of these partial derivatives. We get the determinant of cosine theta, negative r sine theta, and r cosine theta. Now I don't know if we've covered determinants explicitly, but if I want to take the determinant of a matrix A, and A is defined as having elements, A, B, C, and D, then the determinant of A is equal to AD minus BC. So we take this, and then we subtract that for a 2 by 2 matrix. Taking a determinant for a 2 by 2 matrix is very easy. Anyways, we want to take the determinant for this 2 by 2 matrix. So we're going to multiply these two terms, so cosine theta times r cosine theta. We get r cosine squared of theta. Then we multiply these two terms, sine theta times r sine theta negative. We get negative r squared sine, or negative r sine squared theta. But of course we're subtracting this because this is the determinant. Then we can cancel out these negative signs. Then we get plus. So we get r times cosine theta squared plus sine theta squared. Of course that's equal to r because cosine theta squared plus sine theta squared is equal to 1. So we get r times 1, which is 1. So therefore, if I want to take the integral over the f of uv j du dv, then that's going to be equal to the integral over our new region of f of r cosine theta, r sine theta, r dr d theta, okay? So this is the Jacobian in action, right? I start from some xy and some transformation equations. I construct the matrix with the partial derivatives, I evaluate the matrix, I get my constant, and then I transition everything into terms of the new variables, including the bounds of integration. And of course, all we did this for is for this little r term, or this little constant that we get from our determinant. So that is the transformation for polar coordinates. In the next video, I want to cover some examples, and we're also going to look at the three variable case for the Jacobian, the n variable case. We'll look at the three variable case though, considering spherical coordinates, so going from the Cartesian to the spherical case. So thanks for watching, and this will be some of our last videos on multivariable integration, and then we will be moving on to the topic of vector calculus, which is putting everything, absolutely everything we have learned together and